Hello, it's Keith here, and this is the first of the Yquest series of 6502 assembly programming tutorials. Well, what's Yquest? Well, Yquest is a remake of a game I used to play on MS-DOS called Yquest, and I made this during my Z80 live streams, and it was based on the super simple series examples. Remember, we had a smiley face, joystick moved around the screen, and this was a very successful Z80 project, and I wanted to try and port it to the 6502s, and I believe I've successfully done so. You can see a few versions here. These aren't all of them, but this is the Atari Lynx version here. This is the PC Engine, and this is the BBC, and it's out on all the other systems I cover in my tutorials as well, pretty much. So if you are interested, please go ahead and download it and have a look at them. We're going to be going in this series over the basics of how this game works. We're going to discuss very quickly the internal structures, and then we're going to look at the platform-specific code which handles the graphics and the joystick on each system. And altogether, I think that's going to give a great introduction to this game. The idea being, it's free and open source, you can download it and maybe make something your own of it. And as I often say in these tutorials, you're welcome to do that even commercially. I really don't care, and you don't even need to give me credit if you don't want. So if the code's any use to you, please go ahead and use it. Now, the code for the 6502 version has been converted from the Z80 version, very much like I did with Grime. Now, I do this these days. I've got some partial automation. I've got some little software I wrote that converts some of the code, but it doesn't do a great job. So the rest I do myself, and I use some macros and scripts and things. We're going to look at the basics of what the new code looks like. The multi-platform code we'll look at today, and the common code defining the data structures, and I'm going to discuss how the game works in general. But I'm not going to go into a massive amount of detail in the 6502 series. The reason for that is the Z80 series, I did a total of 5 episodes on the multi-platform code, and the code is almost identical from the point of view of the function of each module. The names are the same. The use of registers on the Z80 version and the use of temporary 0-page entries on the 6502 version are identical. There's really not much difference there, and I don't want to create 5 episodes that just repeat exactly what I said last time. So if you're interested in the multi-platform code, please see the Z80 series, and say if you look at the 6502 code as you read that Z80 series, you'll see everything's got the same name, everything works the same. So that's why I'm not covering it like that. What we are going to do today is we're going to go quickly over each module and discuss how they work, what each assembly file does and how I've gone about converting things, and we're also going to just quickly see the game. Then after this episode, we're going to go into the platform specific series, and we're going to look at each of the versions and what has to change for the BBC versus the Lynx, and so on and so forth. So anyway, first of all, let's actually just see the game in action, and let's just quickly discuss what this game actually involves. If I can find one of these that actually wants to start up. Okay, so this is the PC Engine version of the game, and I'm playing typically terribly. It's running a little bit fast actually. PC Engine version maybe needs slowing down a bit more. What we have to do though, we have to collect these crystals, and when we get all the crystals we move to another level. Now I've actually started the game at a very difficult level here. I was doing some testing just to make sure everything worked with regards to the enemy firing. You can see that green enemy over there is shooting away, and I can shoot back as well, and if I kill him he'll disappear for a while before he respawns. We have to collect all of the crystals to get to the next level. Let's say it's just a very simple game. Now on these systems it's currently using the tile map. I do plan on doing a version later on which is going to use the sprites on the tile map systems, but at the moment I wanted to base it as much as possible on the simple series. Just to, a lot of the point of this was to show that such a simple piece of example code could be built into a legitimate, playable game of sorts, and that's what this was designed to do. So as you can see, it works on all these systems irrespective of screen size and graphics capability, and it's basically the same game each time because 90% of the code is exactly the same code in each time. So that's what we're going to be looking at today. So anyway, let's go over to the source code and let's have a look at what we got. So the game code itself consists each time of one platform specific module, in this case Lynx Yquest, PC Engine Yquest, and BBC Yquest. Let me just change my window position here so you can see the labels here. So this is PC Engine Yquest. So this is the PC Engine specific code. Here's the BBC specific code, and you can see there's some definitions here that reconfigure the common modules to make them work accordingly. Now, one problem on some of the systems is the internal resolution that the character's movement occur at, and the visual representation is sometimes not the same. Sometimes it's a much lower resolution display than the actual calculations, and that could cause problems with the collision detection. So we ignore the bits of the collision detection that we couldn't actually draw properly on the screen, so that if the player doesn't think they're overlapping an enemy, well, logically speaking they might be, but they might not be able to see it. So that's a correction for that. And we've got screen size configuration here, and we've got a definition of some area of memory that's called user RAM, and that's used for the game variables, things like where the enemies are on the screen, where the bullets are, things like that. So there's one of those. There is a multi-platform module here. This is all of the code that handles the actual gameplay. You can see there's tons of it here, and as I say, I've gone through all of this in the Z80 series, and things like the label names are identical. The registers, the Z80 registers, are being mimicked with 0-page pairs here, and you can see I've got functions here to mimic the push and pop commands. We're going to have a look at those in just a moment. So that's the multi-platform code. We've got some definitions of the data structure here for the game RAM here, and we've also got a data defs here, which is the actual definitions of the levels and things like that. Now, the reason we were starting at such a difficult level before was because I'd remmed out all the earlier levels as part of my testing, because I needed to test the bullet code. I was doing some optimizations on the code, you see, so I just had to go over that. Okay, so what we're going to do today is we're going to discuss that. We're also going to have a look at very quickly the basic functions and basic macros, which are my common tutorial code. And you can see here we've got modules here to do various Z80 functions, and just to do things a bit more quickly, loading pairs in of the values so that we don't need to define 2 0-page entries every time, which really starts to pad the code out to very confusing levels. Okay, let's start by discussing the RAM definitions then. Now, our objects all use 8-byte definitions, so if we've got 8 bullets on the screen, each of those will use 8 bytes, and they always use the same structure. Now, objects could be the player, they could be enemies, they could be player bullets, they could be enemy bullets. They all use the same structure. They use a sprite number, an unused byte that was just spare, an X and a Y position, an X and a Y acceleration, a program, which is the movement commands. This is mostly for enemies really, and a collision program, which defines how the object will hurt the player or what effect it will have. If it doesn't hurt the player, like a crystal will not hurt the player, it will give the player an extra crystal towards the end of the game. This is also used for objects that are uninitialized if collision is 255, or objects that are dead if it's 254. We've got an X and a Y position, which is to do with the font drawing. We're using a version of the print string routines we saw in the past. They've been modified. We're using a sprite font at whatever color definition the system is, so either 16 or 4 colors in most cases. Sprite frame is to do with the sprites. We've got 4 banks of sprites. There's 16 sprites in total. So this goes from 0 to 3, just switching between the 4 banks. Bullet array is the player's bullets. There's 8 of them, maximum on screen. Enemy bullets is the enemy's bullets, maximum of 8 on screen. You can see each of these is offset from the previous one, and that means that we can just change this starting point and move the entire bank of memory around. And this is because some of the systems are using ROM, which means we can't use self-modifying code, and we can't have variable definitions within our code. We need them in a separate bank, and we need to be able to move that separate bank around depending on the system we're working on. And I actually copied this straight from the Z80 version. I didn't make any changes at all to this, so that was very handy as well. Object array is the enemies, the crystals, the mines, the things on screen. Invincibility is how long before the player can be hurt. Random seed is to do with the random number generation. Key timeout, well, if you're holding down up, down, left or right, you will start accelerating. To reduce the amount of speed you accelerate by, there's a key timeout, and during that it will ignore any more presses. Lives are how many lives the player's got. Level is the current level. Crystals, the remaining level crystals. Playing SFX and playing SFX2 are the sound. It's using Chibi sound again. This is the sound driver I've covered in the platform specific series. High score is a binary coded decimal, as in score. That's 8 digits, 4 bytes. It's a packed format, and we've got some code to do that. We've got our player object, which is in the exact same format as defined here. That's the player, obviously. And we've got a last position, and that's used for moving and updating objects. And that code very much mimics the code that we saw before in the simple series when we were moving that smiley around the screen. It was based on that code. So that's the RAM definitions. The data definitions, these define the things that we need to have constant. So we've got the player object back up here. This is the starting position of the player after the player's died. It just defines the middle of the screen and resets everything else. We've got some definitions here that are constants for the game. The number of crystals we can show, the number of enemies, these never change. Here we've got pointers to the level map. There's 16 levels, after that it loops. Each level definition looks like this. First we've got the number of crystals on the level, then we've got an unused byte, and everything else is then a type and a count. So this is 3 of object type 1, this is 3 of object type 2, and this is 255 of object type 0, which is effectively the end of the definitions for that level. Now these level definitions all use these object types, and the object types are defined down here, and they're in this format shown here. They're not quite the same format, maybe they should have been, but they weren't. So we've got a sprite type here, a collision program, which is usually 0, and we've got a program and an X and a Y speed and acceleration. The starting positions are always random, you see. So these are our object types that we can have, and they're all enemies except for the crystal and the empty object, which is defining the end of the list. You can see that just here. So these are used by our code to define the objects for each level as the game progresses. There's some random numbers here for the random number generator. We've got some strings, messages. There's shorter versions for our very small screen for the links. Those are shown to the screen. And here we've got some binary coded decimal scores. Depending on when we sort of collect crystals and things, we will get extra score. And here we've got a title picture here for each of the systems. Of course, these are different sizes depending on the screen size, and we're going to use these to show our Yquest logo to the screen, the different versions of it. Okay, now all of these are used, of course, by the multi-platform code. We'll go over this just very quickly and discuss each section. As I say, please see the Z80 series for more details. We've got a random number generator here. This generates 8-bit pseudo-random numbers, although it uses a random seed that's quite random, so they will actually be pretty random in this case. This random number generator was actually created for Chibi Aliens, and it allows it to produce repeatable random numbers, so you can produce predictable results based on a random seed. But in this case, we're not using it for that purpose, but it is a pretty random. It produces all the values from 0 to 255 with reasonable randomness, and so it's fairly reliable, and that's why I used it for this program. Now, safe randomized object position will produce a random position for an object that's not overlapping an existing one. Range test will check if two objects are overlapping, defined by a particular range. So for example 3, 6, x, y range are two objects within that range, or a wider range of 5, 10. So this is for things like when we're initializing new objects, checking they're not overlapping, or checking if a bullet or a player has hit an enemy. And that's what those are used for. So this will just check that, and it will return a 1 if there's a collision, or a 0 if there's a no collision. That was more convenient for the 6502. The Z80 actually returned a carry or no carry flag, but for this one I felt this was better, 1 and 0. That's what I've done there. We've got ranged random here. This is for producing random numbers, and then we actually build this up into a routine that will select an edge for the objects to appear on, because when an object's killed in the middle of the screen, it will reappear at the edges. So that's how we do it, and that's what these random number generators are for. So in some cases we're randomizing the entire object position. In other cases we're just randomizing an edge to start on. We've got a print space and a locate and print string routine. The printing routines are not firmware, of course. They are using a bitmap font in the native format, so effectively we're using the sprite routine for the bitmap font as well, and that was very beneficial because it meant that we could use the same code. Draw UI will show all of the text to the screen, things like the lives, the crystals, the level and the high score. Those all get onto the screen with this routine. Level init will start a new level. This will read in from the definition, and it will define all of the objects that appear in the level, things like the crystals and the mines, and also of course the enemies. That's all defined by this routine here. Reset player will center the player to the middle of the screen and set the invincibility. This is for if the player's just been hurt. Draw player will actually redraw the current position of the player. Draw and move, this will handle the movement of objects, all kinds of objects really. So this will first draw the player bullets, then draw the player, then calculate collisions between the bullets and the enemy objects. Then it will handle the movement of all the enemy objects as well. And finally it will handle the enemy bullets. So that handles all of the movement basically, and it also finally plays the sounds. We've got a small routine here for giving the player any score, and this is the routine that handles the movement and drawing of the objects themselves. So this is things like the bullets and also the enemies. Now there are multiple programs depending on how we want the enemies to move. Each one is numbered. Program 6, for example, will seek onto the player, but most of the others are just different speeds, firing routines, and random direction changes. It's pretty straightforward, really. And as I said before, if you want to see more of that, please see the Z80 series where I went into that in more detail. Now, finally, once we've done that, we are then just checking the player is still, the object is still on the screen. Again, this is copied directly from that original simple series. And so, as I say, it's just showing that we can use something as simple as that and build it into a proper program. Here we've got a few routines to simulate commands that the Z80 was using. So we're using IY in some cases to point to our objects that we're testing and things, and we needed an ability to move through the IY and IX ranges here, so we've got some functions that do that. Here we've got the routine that tests if the player's hit an object here. Here we've got the one that gives the player an extra crystal. Here we've got the one that handles the player being hit by an enemy, and here we've got the game over message. Down here is the next level. This is what happens when we proceed to the following level if we've collected all the crystals. Here we've got the routine for if the player wants to fire a bullet. We have to check first if there are any bullets left, because 255 is an empty slot in the bullet array. And then there's the same for the enemy bullets down here. As I said before, all of these are in the Z80 tutorials, so please see those if you want to see more detail on those, because I really don't want to spend a couple of hours going through them all again, because the description will be identical. It's just the code is only slightly different. Now, in all of this code, of course, there's a lot of routines like push pair, push X, pull X. These are macros that I've used to simplify things, and you'll also see some jumps to subroutines that are doing things to help me out to mimic functions that the Z80 has that, of course, the 6502 does not. Now, I know some people won't be a fan of that kind of thing, but to be honest, I'm coding so many systems now, so many different CPU types, I'm struggling to even remember them all. So I'm having to sort of make simplifications to allow me to program effectively with as few bugs as possible. So it's just, unfortunately, it's just the nature of the beast at this stage. Now, if you look at the macros here, you'll see I've got various routines here. One's for loading X and Y simultaneously. Loading a pair here, this will alter the accumulator. Load pair safe, which will leave the accumulator intact. I've got push pair, pull pair, push pair safe, pull pair safe and things. These again are all routines that are being used to simulate Z80 functions or to just reduce the amount of time that it takes me to do jobs. Things like loading a pair, a 16-bit pair into 0-page entries, having 4 lines to do that every time when the equivalent Z80 command would have been a single line was making the code very long and complicated. So I'm using those as well just to simplify things down a little bit. As I say, generally I'm not a fan of that kind of thing, but I do need to try and make sure the 6502 version isn't harder for me to program than the Z80 version, because it's the Z80 I'm more familiar with. And here you can see the 0-page entries I'm defining as being simulating the Z80 registers that I'm more used to. And you can see also there's various functions here. There's the print string routine here, and also some other functions like the CLDIR command, which is for clearing areas of memory. This is something we have to do quite a lot, so having it in this common area. Incrementing pairs of registers here, we've got a call to do this for us, again just to save a little bit of memory here and there, because these are something I do need to do quite often. And as I say, those are helping me out with my coding quite a lot, and they did allow me to convert this program in just over a week. The first BBC version was done in about 7 or 8 days, and I've got all of the 6502 versions ported in just 2 weeks. So, and that's not 2 weeks of 9 to 5, obviously that's just a few hours in the evenings, and you know, maybe half a day each day at the weekends, something like that. So it's been very successful, really, and I think it's sort of firstly it shows that if you've got Z80 code, it's easy to port it to 6502 potentially, and also, as I say, if you're a beginner just getting started, this is a game you can produce very quickly. Now, if you're interested, I did a Z80 live stream series where I wrote the original game, and you can see all of the mistakes and challenges I had there if you want to see that. But apart from that, if you want to just see more of this, please stick around. We're going to be looking at each platform, and we're going to go into the modules that make up each one, and the changes that have to be made for each system, because working on a system like the Atari Lynx with its tiny little screen is very different to working on a system like the NES with tiles and sprites. And with regards to the NES and the SNES, we're actually going to extend our simple series, and we're going to start using a cache so that we can not have to wait for VBlank every time we draw to the screen. We're going to cache it all and do it all during the VBlank. So that will be interesting for you if you're into those systems. Anyway, though, I hope you found this interesting. If you have, please like and subscribe. If people like the videos, then YouTube recommends them more to other people who might like them as well. So it really helps me out if you do that. Whatever you do, though, I hope you have a lot of fun with your creative projects, and I wish you all the best. I hope to see you soon. Thanks for watching today, and goodbye.